In 1985, a state-of-the-art radiation therapy machine called the Therac-25 began delivering massive, fatal overdoses of radiation to patients. The machine itself was a physical behemoth, but its failure didn't come from a mechanical breakdown. It happened because the manufacturer replaced rigid physical safety interlocks with abstract software controls. Decades later, an entirely different kind of vulnerability was discovered in GitLab's architecture, CVE 2022-4037. This was a highly sophisticated web exploit that allowed attackers to hijack accounts by manipulating the system's email verification process. These two failures occurred in different eras of computing, across different architectures. Yet the embedded medical device and the modern web application failed for the exact same reason. This diagram illustrates the assumed state machine model. Developers look at an operation, like a login or an email update, and assume the request transitions cleanly and instantaneously from state A to state B. This is the fallacy of atomic execution. But the reality of the architecture is far more complex. A single HTTP request actually pushes an application through a sequence of fleeting, invisible intermediate steps called substates. Real execution environments process thousands of tasks concurrently. When software treats a multi-step operation as a single instantaneous event, it leaves those microscopic substates exposed, creating a mathematically exploitable attack surface. To see how these substates are weaponized, we deconstruct the Ruby on Rails framework device used by GitLab. The attacker's objective here is specific: change an account's email address and intercept the system's confirmation token. Normally, an email update triggers a secure sequence. It receives the new email, updates the database, generates a security token, and sends an email to the user. This is the code execution flow. On the left, the framework updates the user's unconfirmed email directly in the database. Immediately after, a secondary thread queues the email template and generates the confirmation token on a parallel timeline. The flaw? The system passes the destination email as a temporary variable in memory, but to generate the actual confirmation token, the template engine reads back from the database. A distinct 1 millisecond physical gap opens between the two operations. This tiny window is the exploit vector. An attacker sends two concurrent requests to land the second exactly within that 1 millisecond gap. If exact, the collision occurs. The second request aggressively overwrites the database email value before the read operation. The system gets confused by its own parallel processes. It generates a valid confirmation token for the first email, but routes it to the second address controlled by the attacker. Whenever an application mixes transient memory data with persistent database reads, the execution stops being predictable. It creates a highly exploitable substate collision. If these 1 millisecond windows exist across enterprise applications, they should be exploited constantly. For years, they rarely were. The reason is physical networking. As TCP packets travel across oceanic fiber optic cables, they fragment, separate, and stretch chaotically through different network nodes. This erratic delay in packet delivery is known as network jitter. It is the primary physical obstacle to synchronizing code execution remotely. Hackers previously relied on techniques like last byte sync to time their requests. Because of network jitter, even the best efforts result in a 4 millisecond spread between packet arrivals. Squeezing two concurrent requests into a 1 millisecond window over a 17,000-kilometer connection is a mathematical impossibility. The packets simply arrive too far apart. Geographical distance and network degradation were the only factors protecting these logic flaws. Back-end developers operated under a false sense of security, assuming their substates were mathematically unreachable.
That false security evaporated when security researcher James Kettle developed a new methodology. He engineered a way to bypass the operating system's network stack entirely and eliminate jitter. This illustrates the necessary protocol for the exploit. It relies on HTTP/2 multiplexing, allowing multiple parallel request streams to share a single connection pipe. The attack begins by pre-sending the bulk of 30 concurrent requests to the target server, but the attacker explicitly withholds the final byte of data. The HTTP/2 end stream frames are kept locked inside a local buffer. The target server receives the incomplete data and provisions 30 open processing threads, but it has to idle, waiting for that final byte to mark the requests as complete. Next, the attacker disables Nagel's algorithm by toggling a setting called TCP-NODAY.
This algorithm normally batches small packets unpredictably to save bandwidth. Disabling it stops the operating system from interfering with the timing. The attacker then dispatches a benign ping packet to warm the local TCP connection, ensuring the network stack is ready to fire instantly. Finally, the gate opens. The attacker bypasses the delay and pushes all 30 withheld end stream frames simultaneously, launching them as one massive, coordinated strike. With Nagel's algorithm disabled and the connection warmed, the operating system packs all 30 frames into one single TCP packet. It travels across the internet as a unified block. When that packet hits the destination server, it unpacks. The server registers 30 completed requests at the exact same microsecond. The single packet attack mathematically neutralizes network jitter. What used to be a statistical anomaly is now a highly reliable, perfectly repeatable exploit. Attempting to patch race conditions with standard rate limiting or application layer logic checks is completely ineffective against single packet attacks. By the time the software detects the anomaly, the concurrent requests have already collided. This brings us back to the failure of the Therac 25. The engineers removed rigid safety mechanisms, trusting that their software logic was flawless. The results proved that abstract logic cannot replace physical constraints. If an architecture operates without physical or hardware locks, the underlying software must be engineered to be strictly deterministic. For backend developers, this requires two specific architectural mandates. First, never mix disparate data sources, like transient memory variables and persistent database reads during a state transition. Second, rely entirely on strict database transaction locks. Simple session batching is not enough. If two requests operate on the same record simultaneously, one will still overwrite the other. To systemically prevent these undefined behaviors, engineering teams use rigorous baselines like the SEI Cert-C coding standards. These rules exist to disallow the vulnerable code constructs that allow these collisions to occur. Defending against substate manipulation requires abandoning reactive code patches. Systems must be built with proactive, network-wide architectural determinism. This level of strict locking has to be enforced algorithmically inside the CI/CD pipeline, long before the code ever reaches production. Enterprise static analysis tools built for cert compliance automate this process. They parse the application logic to detect the invisible, unlocked substates that human reviewers miss. The modern race condition has now evolved into a highly complex topological vulnerability that systematically dismantles application logic from within. The assumption that a request executes instantly and cleanly is a deadly fallacy. Nothing in a concurrent execution environment is atomic by default. System architects must respect the state machine. Every API endpoint must be engineered under the assumption that it exists in a hostile, hyper-concurrent environment.